In this episode, we're going to take two network problems that look simple on the surface but can waste hours when you don't have a clean mental model. Failures in Dynamic Host Configuration Protocol, DHCP, and conflicts where two devices end up trying to use the same Internet Protocol, IP address. These issues are common in real environments because they sit right at the point where a machine becomes reachable, and when that point fails, everything built on top of networking fails too. What makes them tricky for beginners is that the symptoms often show up as vague application errors rather than a clear message that says DHCP is broken or you have an address conflict. The goal is to build practical logic you can apply quickly, where you identify the most likely category based on what you can observe, and then choose a next step that reduces uncertainty rather than adding noise. With that approach, you can isolate whether you are dealing with missing configuration, wrong configuration, or competing configuration. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A strong foundation begins with understanding what DHCP is actually doing for a typical machine on a typical network. DHCP is the system that automatically provides a host with basic network settings, including an IP address, the default gateway to reach other networks, and the DNS servers needed for name resolution. The reason it exists is convenience and consistency, because manually setting these values on every device would be slow and error-prone, especially when devices move between networks. When DHCP works, it is mostly invisible, which is why people notice it only when it fails. When it fails, the machine might still have a network interface that looks physically connected, but it lacks the logical details needed to communicate properly. Beginners sometimes confuse link status with network readiness, but link status is only the physical layer and DHCP lives above that. A machine can be plugged in and still be effectively isolated if it never receives a usable configuration. One of the fastest ways to reason about DHCP failures is to separate three symptom families that often get mixed together: no address at all, an address that exists but is wrong for the network, and an address that looks plausible but still cannot communicate beyond a small scope. If the host never obtains an address, the system often falls back to a self-assigned address or shows an unconfigured state, which usually means it cannot talk to anything beyond itself. If it has an address, but it does not match the network you believe it is on, that suggests misassignment, such as the host receiving an address from the wrong DHCP server or using a stale static configuration. If it has an address that matches the local network, but it still cannot reach a gateway or other hosts, that suggests either the gateway information is missing or incorrect, or traffic is being blocked at a different layer. The key beginner habit is to avoid jumping straight to DNS or firewalls before confirming whether the host's basic addressing makes sense. Addressing is the first contract, and without it, higher layer troubleshooting is wasted effort. When DHCP fails, it can fail on the client side, on the server side, or in the path between them, and that is why the best next step is usually the one that helps you locate the failure domain. On the client side, the host might not be requesting an address correctly, might be using a corrupted configuration, or might have an interface state that prevents proper negotiation. On the server side, the DHCP service might be down, misconfigured, out of available addresses, or restricted by policy. In the path between them, network segmentation, relay configuration, or filtering can prevent the DHCP exchange from completing. You do not need to know the exact packet format to reason well here. You only need to know that DHCP relies on messages that must reach the right server and return. That suggests a high-value logic move. Compare whether multiple devices on the same segment are failing in the same way. If many devices cannot obtain leases, suspicion shifts towards server availability or path policy. If one device fails while others succeed, suspicion shifts toward the client or its local connection. A major reason DHCP problems feel confusing is that partial configuration can look like total failure. For example, a host might receive an IP address, but not receive correct gateway information, which can make local communication possible while external communication fails. Beginners often interpret this as routing being broken everywhere, but the reality is that the host simply does not know where to send traffic for non-local destinations. Another partial failure is receiving an IP address and gateway, but receiving incorrect DNS servers, which makes address-based connectivity work while name-based connectivity fails. In those cases, the machine is networked, but the experience feels broken because most user actions start with names. A COM triage approach treats these as evidence. If some connectivity works and other connectivity does not, you examine which configuration elements are missing or wrong rather than assuming the whole network is down. This is the logic of narrowing, where you use what still works to identify what contract is failing. DHCP is often the supplier of that contract, so its failure can be complete or partial depending on what it provided. Now let's pivot to IP conflicts, because conflicts create a different style of symptom and demand a different first response mindset. An IP conflict happens when two devices attempt to use the same address on the same network, which breaks the assumption that an address uniquely identifies a host. In a local network, devices use Address Resolution Protocol, ARP, to map an IP address to a Media Access Control, MAC, address, which is the hardware-level identifier used for delivery on that segment. When two devices claim the same IP, ARP mappings can oscillate, meaning traffic meant for one device may be delivered to the other depending on which one most recently announced itself. That produces the classic symptom of intermittent connectivity, where sometimes the host appears reachable and sometimes it does not, or where a connection seems to land on the wrong system. A beginner might blame flakiness in the application, but the underlying truth is that the network cannot consistently decide which device owns that address. Conflicts therefore feel chaotic not because the network is random, but because two realities are competing. One way to distinguish a DHCP failure from an IP conflict is to pay attention to stability over time. DHCP failures often produce consistent, repeatable inability to obtain a valid configuration, meaning the machine behaves broken in a steady way until configuration is corrected. IP conflicts often produce unstable symptoms, where connectivity works briefly, then fails, then works again, sometimes correlating with the other conflicting device coming online or going offline. Another clue is scope. A pure DHCP failure on one host affects that host's ability to communicate, while an IP conflict can affect multiple parties because it creates confusion for anyone trying to reach that address. The next step logic differs accordingly. With DHCP suspicion, you focus on whether the host has a valid lease and whether the network is providing correct parameters. With conflict suspicion, you focus on identity collision and on which device is currently winning the ARP battle. Even as a beginner, you can reason about this without tooling by listening to descriptions from users, observing whether failures come and go, and checking whether the problem appears only for one address. A common source of IP conflicts is mixing static assignments with dynamic leasing without coordination. If a device is manually configured with an address that the DHCP server believes is available to lease, eventually the server may hand that address to another device, creating a collision. Another source is duplicate imaging or cloning, where multiple devices are deployed with the same network configuration, including the same static address, so conflicts are guaranteed when they appear on the same segment. Conflicts can also occur when a host wakes from sleep or returns from a different network with stale assumptions, attempting to reuse an address that is now legitimately assigned to someone else. Beginners sometimes assume conflicts are rare, but in environments with many devices, frequent changes, and imperfect inventory, they are surprisingly common. The operational lesson is that address management is a governance problem as much as a technical one, because you need a consistent policy for what is reserved, what is dynamic, and what is safe to assign manually. When that policy is weak, conflicts become a recurring form of chaos. DHCP itself can indirectly cause conflicts when it is misconfigured, especially if multiple DHCP servers respond on the same segment without being coordinated. In that scenario, two different servers might offer different leases, or one might offer addresses that overlap with the other, creating unpredictable behavior. A client might accept a lease from one server one moment and a lease from another server later, depending on timing and reachability, which makes the host's identity unstable. This can look like a conflict because the address changes unexpectedly or because the host appears at different addresses over time, confusing caches and security policies. The key reasoning move is to consider whether the environment is supposed to have one authoritative DHCP source and whether the observed behavior matches that expectation. If many devices show inconsistent addressing, it is less likely that every client is broken and more likely that the addressing authority is inconsistent. This is also where best next step logic often points toward comparing behavior across devices, because patterns across multiple hosts reveal network-level issues far faster than staring at a single failure. The same troubleshooting principle applies here as elsewhere. Shared symptoms often come from shared control points. Another subtle but important symptom category involves the default gateway, because gateway reachability is a central dividing line between local-only success and true network access. If a host has an IP address but cannot reach the gateway, then nothing beyond the local subnet will work, and many applications will time out in ways that feel like server outages. This can happen if the gateway address provided is wrong, if the gateway is down, if the host is on the wrong subnet, or if local filtering prevents reaching the gateway. A conflict can also target the gateway address itself, which is a particularly disruptive case because it affects an entire segment's ability to route externally. Beginners often forget that the gateway is just another address on the local network and can therefore be impacted by the same kinds of collisions and misassignments. The calm approach is to treat gateway reachability as a critical checkpoint in your logic. If the gateway step fails, you focus on local addressing and local network path first, rather than chasing remote service issues that are downstream. This is how you keep troubleshooting efficient and prevent a simple local misconfiguration from turning into a long detour. From a best next step perspective, DHCP failures are often best approached with a question about whether the host is failing to request, failing to receive, or receiving incorrect parameters. If a host fails to request, you suspect client-side issues such as interface state, configuration corruption, or local policy. If it requests but receives nothing, you suspect the path, including segmentation and filtering or server availability. If it receives a configuration that is clearly incorrect, you suspect server-side configuration or multiple competing servers. For IP conflicts, the best next step question is whether the address is supposed to be dynamic or static, because that tells you where the collision likely originated. If the address is dynamic, the DHCP pool and reservations become the primary suspect. If it is static, you suspect manual duplication, stale documentation, or improper reuse. In both cases, you aim for the step that reduces uncertainty most, which is usually confirming whether the issue is isolated to one host or shared across a segment, and whether the symptom is stable or oscillating. That logic keeps you from overreacting and helps you communicate clearly to others, such as saying this looks like a least distribution problem rather than an application outage. It is also worth addressing beginner misunderstandings that cause unnecessary risk during these incidents. One misunderstanding is assuming that switching to a static address is always a safe workaround when DHCP is failing, because that can solve one machine temporarily, but can also create new conflicts if the static address overlaps with a dynamic pool. Another misunderstanding is assuming that a conflict can be solved by simply rebooting, because rebooting might temporarily change which device wins the ARP mapping, making the problem seem fixed until it returns. A third misunderstanding is assuming that if one service fails, the network is down, when the real issue is that name resolution or gateway configuration is incomplete. These misunderstandings matter because they push people toward actions that hide the real problem and increase long-term instability. The healthier approach is to treat workarounds as controlled and documented, with awareness of how they might interact with DHCP policy and address allocation. Even as a learner, adopting this cautious mindset is important because it trains you to preserve reliability rather than to chase immediate relief at any cost. When you step back, you can see that both DHCP failures and IP conflicts are really about identity and trust on the network. DHCP is the mechanism that gives a host its network identity and tells it what relationships exist, such as where the gateway and DNS servers are. IP conflicts break the uniqueness of identity, making it impossible for the network to consistently deliver traffic to the correct endpoint. Both problems therefore create cascading symptoms that touch everything from logins to package downloads, which is why they are so important to isolate quickly. The best next step logic you are building is not about having a huge toolbox, but about having a clear sequence of questions that separates configuration absence from configuration mismatch and stable failure from oscillating collision. This approach also helps you communicate during incidents, because you can explain what layer is failing and why the symptoms make sense. Clear explanations reduce thrash, and reduced thrash is a form of reliability. As we wrap up, the key outcome is that you can look at a messy connectivity complaint and quickly decide whether you are dealing with a failure to obtain a coherent configuration or a collision between two devices claiming the same identity. Dynamic Host Configuration Protocol, DHCP. Failures often produce consistent inability to obtain a valid IP address, gateway, or DNS configuration, and partial failures can create misleading symptoms where some connectivity works while other parts fail. Internet Protocol, IP, conflicts produce unstable, intermittent behavior because Address Resolution Protocol, ARP, mappings can flip between competing media access control, MAC, owners of the same address, making traffic land unpredictably. The best next step logic relies on scope, stability, and comparison across devices, because shared failures point to shared control points like DHCP servers or segment policy, while isolated failures point to client-specific conditions. When you practice this reasoning, you stop treating these incidents as mysterious and start treating them as identity problems with clear, evidence-driven branches. That is the kind of calm troubleshooting maturity Linux Plus wants you to demonstrate, because it shows you can isolate the category quickly and choose actions that reduce uncertainty without creating new damage.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.